Welcome to This Explainer. All right, we're diving straight into mastering 3D symmetry today. I want you to start by picturing a bright, colorful 3D cube rotating right in front of you, just to anchor our lesson. Look, whether you're studying for a 10th grade geometry test or you're just trying to wrap your head around spatial reasoning, finding planes of symmetry can sometimes feel like trying to solve a puzzle completely blindfolded. But today, we're going to unpack the ultimate counting strategy that works absolutely every single time. First up, let's make sure our foundation is rock solid. What exactly is a plane of symmetry? It's basically an imaginary flat surface that divides a 3D solid into two halves that are perfect mirror images of each other. Imagine passing a perfectly flat, sharp slice straight through that colorful 3D cube we just talked about. If it's a true plane of symmetry, the pieces on both sides of that cut are going to match exactly in shape, exactly in size, and exactly in their relative position. It is precisely like looking in a mirror. So, okay, we know what a symmetry plane is, but here's the classic trap that catches honestly almost everyone. How do we systematically count every single one in a complex shape without double counting or missing one that's hidden right in plain sight? When you're staring at a 3D object, it's remarkably easy to lose track of which ways you've already sliced it in your mind.
Here is our roadmap for this explainer. We'll cover 1. What a symmetry plane is, 2. Regular versus non-regular solids, 3. Slicing faces and edges, 4. Pyramids and vertices, and 5. Curves and infinite symmetry.
Section 1. What is a symmetry plane? Establishing the core strategy.
To successfully find all these planes without missing a single one, you need a systematic approach. You really can't just guess. To track down all the planes for literally any 3D solid, we follow 5 exact steps. First, identify regular versus non-regular properties. Second, find planes parallel to pairs of opposite faces. Third, find planes slicing diagonally through edges. Fourth, find planes passing through vertices and base midpoints. And fifth, check for infinite rotational symmetry. We look for these structural anchors to guide our imaginary knife.
Section 2. Regular versus non-regular solids. Knowing your shape. Before you make any mental cuts, you've got to know exactly what kind of solid you're dealing with. This comparison brilliantly illustrates why a regular shape, like our cube, has way more symmetry than a non-regular shape, like a rectangular block. Regular shapes have equal sides and identical faces, and that equality, it means they can share symmetry planes across a ton of different face and edge combinations. Non-regular shapes, however, have unique features, like one side being longer than another, and that severely restricts your symmetry planes to only those matching dimensions.
Section 3. Slicing faces and edges, the box cuts.
All right, here's where the visualization gets really fun. We're going to apply our steps to perform what I call the box cuts. First, we look for planes parallel to pairs of opposite faces. You do this by passing an imaginary slice directly halfway between two parallel congruent faces. Think of slicing a block of cheese right down the middle so the left and right sides are totally equal. If you do this halfway between parallel faces, a rectangular cuboid, which has 3 pairs of opposite parallel rectangles, yields exactly 3 planes of symmetry. Our perfect cube, with its 6 identical faces, also gives us exactly 3 planes using this specific method. But here's where that regular versus non-regular property we talked about completely changes the game. Next, we find planes that slice diagonally through edges. Think about cutting a standard plane die diagonally from one corner edge all the way through to the opposite edge. Because a cube has 12 equal edges that form 6 pairs of opposite parallel edges, slicing across each pair gives us 6 entirely new diagonal planes of symmetry. But what about the cuboid? The rectangular prism actually fails this test. Why? Because its adjacent sides have different lengths. If you slice it diagonally, the two halves are asymmetric, meaning if you folded them over that plane, the corners wouldn't perfectly line up. So, combining the 3 parallel planes we found first and the 6 diagonal planes we just found gives a perfect cube exactly 9 planes of symmetry. 9! Meanwhile, because those diagonal slices create asymmetric halves, a non-regular rectangular prism, it maxes out at a total of only 3 planes. That is a massive difference, just because the side lengths aren't equal.
Section 4. Pyramids and vertices. Pointing to the base. So, box cuts won't work on shapes without opposite parallel faces. Instead, we have to look at the vertices. For a shape like a square pyramid, you find symmetry by dropping a vertical slice straight down from the top apex, the very tip of the pyramid. Imagine a laser pointing straight down through the center to the base.
You then pivot that vertical slice across the base to see exactly where it creates perfect mirror images.
Take our square pyramid. By pivoting that vertical plane, we can drop slices through the top apex and diagonally right through the opposite corners of the square base. That gives us 2 planes. Then, we pivot again and pass the vertical slice through the apex and straight through the midpoints of the opposite base edges. That gives us another 2 planes. Add those up, and this clever pivoting step gives the square pyramid a grand total of 4 planes of symmetry.
Section 5. Curves and Infinite Symmetry. The Circular Advantage. What happens when we leave straight edges in the dust and look at continuous curves? Well, a circular base gives a shape a massive advantage: infinite rotational symmetry. Let's compare a right circular cylinder, like a tin can, to a right circular cone. Because the base is a perfect circle, you can cut vertically down the center from any angle you want. Both the cylinder and the cone have infinite vertical planes of symmetry. But what about horizontal cuts? Imagine slicing that tin can horizontally right through its waistline. You get a perfect mirror image top and bottom. That's one horizontal plane for the cylinder. But a cone? If you slice it horizontally, the pointy tip is entirely asymmetric to the wide, flat base. So the cone gets 0 horizontal planes.
And that brings us to the absolute king of symmetrical shapes, the sphere. A perfectly round sphere doesn't just have an infinite number of planes in one direction. It can be cut from absolutely any angle from any direction as long as your slice passes exactly through the dead center. This brilliantly illustrates how continuous 3D circularity unlocks a literally infinite number of symmetry planes. It is the ultimate symmetrical solid, no contest.
All right, this breakdown brings all our steps and shapes perfectly together into one cheat sheet. We've got our cube at 9, our rectangular prism at 3, our square pyramid at 4, our cylinder at infinite plus 1, and our cone and sphere sitting at infinite. You'll definitely want to pause this explainer right now and snap a picture of this. It's the ultimate study guide.
So, the crucial takeaway from our explainer today is this: always rely on structure, not guesswork. Whenever you're staring down a new 3D object, run through this specific 4-step checklist. Count your face bisecting planes, count your edge bisecting planes, count your vertex bisecting planes, and finally, look for continuous curves for those infinite central axis planes. Following this exact order guarantees you will never miss a plane, and you're never going to double count one either. Now that you're armed with the ultimate counting strategy, it's time to put it to the test in the real world. Just take a look around the room you're in right now. From your smartphone to your coffee mug to the very room you're sitting in, what hidden planes of symmetry exist in the everyday objects sitting right in front of you? Keep looking for those angles and keep exploring.